So here are the success criteria for today's lesson. We're going to look at an identity called the double angle identity. There's one for sine and one for cosine. So success criterion one is, can you identify them? Can you see them? And the second one is then using all the identities to solve trigonometric equations without a calculator. So let's just talk about the two identities we've covered so far. We've really only looked at two. We've looked at this one here, which is that if I take the square of an angle and take the sine of it, sorry, if I take the sine of an angle and square it, and then take the cosine of the same angle and square it, then the result is always 1. Okay, and the other identity we've looked at is, oops, I'll just start off with the left-hand side, would be smarter, that the tan of an angle is exactly equal to the sine of that angle over the cos of that angle, like so. So these are identities, and by identity we mean that for any input to those functions, so for any angle x, that equation holds true. That's what an identity is, okay? These are specifically trigonometric identities, so we have the input being an angle, and then the sine, the cos, or the tan being the output of those three functions, and those relationships hold true, always, 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 even if x is 173 million degrees. Okay, they are always true. Any questions about those two? And sometimes you'll hear that the sine squared plus cos squared equals 1 is the Pythagorean identity, in that you can, it's sort of, the relationship is established by looking at a triangle of hypotenuse 1, that's from the unit circle, and then one of the sides would be cos x and the other side would be sine x. Anyway, we've looked at that before, so I won't go through that anymore. So the double angle identity formulas are given in the textbook with an explanation as to how they are created. And if I've got time, I'll try and find or do a video which explains why the double angle identities work, but I don't really have time in class to go through it. But suffice to say, first of all, what is the sine of 30 degrees? Pi on 6 is what 30 degrees is, but I'm looking for the sine of that angle. 1/2, a half. So the sine of 2 times 30 degrees would be 2 times a half, which is equal to 1, right? No, of course not. So if sine of 2 times 30 degrees is just the sine of 60 degrees, which is equal to √3 on 2, right? So I guess what I'm saying here is that doubling the angle on the inside doesn't necessarily have a direct relation. There's no exact relationship between the two, just by observation. I mean, there is a relationship, but just by observation, you can't just magically multiply it by √3 or something like that. It doesn't work like that. So if we do have an angle that we don't know, like this, it would be useful if we could break down that 2x in the middle to something which we can use. So that brings us to the double angle identities, which are more frequently used than you could possibly think, maybe, but which is why we learn them. So I'm going to go for the cosine double identity angle first. Oops. And the cosine double angle identity is simply this, that if I have the cosine of 2 theta, so I've got a double angle in there, the cosine of 2 theta is equal to, I mean, this is the one that I would probably remember straight up, cos squared theta minus sine squared theta. That's it. That's the double angle identity. That is always true. But there's a couple of little relationships that are equivalent to that one, which I'm just going to explain, and they are in the textbook, but they're pretty straightforward. And that is, so I'll just put a dotted line under that, so you can say that's to me, that's the main identity. But you've got a couple of things that come out of it. So if I look at cos 2 theta is equal to, I might just zoom out so we can see those identities on slide 2 as well. So cos squared theta here, oops, here, is also present in this Pythagorean identity up here. And is it okay if I just say that, look, that from this identity, cos squared theta is 1 minus sine squared theta? Is that okay? Just by taking it to the other side. So if we look at cos squared theta and we replace it with 1 minus sine squared theta, then can you see that we've got 1 minus sine squared theta minus another sine squared theta? So we've actually got 1 minus 2 sine squared theta. Cool. So that's another expression of the cosine double angle identity. But you can see that if you sort of, I mean, not that you have to remember anything really, but if you know the top one, you can always work out the other two. And then I can do the same sort of thing with sine squared theta. That sine squared theta is equal to 1 minus cos squared theta, simply by subtracting cos squared x from both sides. So if I then take my double angle again, then that would be cos squared theta minus, just definitely make sure you've got the brackets in for this one, 1 minus cos squared theta. And that's equal to, just to confirm what we're seeing here, cos squared theta minus cos squared theta gives me 2 cos squared theta, and then the minus 1 at the end there. So there's the two other relationships, I suppose, the two other forms of the same identity. What do you reckon? Is that okay? Any questions about that? The cool thing is that if we know the sine, or in this case, the cosine of an angle, then I can work out the cosine of double that angle by using that relationship. So if I knew that, I'm just trying to pick a sensible one. I can't think of it on the top of my head because I don't know the fractions well enough. But let's just say I knew that the sine of theta, the sine of 15 degrees was 1 on 9. It's nothing like that, but let's just say it was. Then I can use this relationship to work out what the cosine of, I don't pick 15, that was a dumb choice. The cosine of 10 degrees was, say, 1 on 9. Then I would be able to work out what the cosine of 20 degrees is using that relationship, okay? So there you go. But I'll go through an example to make that a bit more clearer. But I also suppose I could also, I guess the other thing I could do, I just thought of this as I was talking actually, I could also do things like, if I know what the cos of 30 degrees is, which we do, it's root 3 on 2, it means I can sort of use these relationships here to work out what the cosine of 15 degrees is. It's by halving it, you see. So that's the sort of thing that we might use it for. Okay, so if you finish filling that out, I'd like to go to the sine one. All good, Ashley? Yep. Okay, so the sine identity rule. It's just got one form. And the sine double identity is the sine of 2 theta is equal to 2 sine theta cos theta. Now, I know that these identities are mathematical because I haven't explained why they are what they are, but technically you don't actually need to know anyway why it is. If you're happy to accept it on faith, more power to you. But like I said, if I remember to and I've got time to, I will stick a couple of explanatory videos as to why those identities do work. But it is in your textbook as well. Is it the sine of theta cos theta? Is that what you're saying? No, it's sine theta times cos theta. Yep. Okay. So what I'd like to do now is I'd like to go through an example. And this example will take us through a few different sorts of tips and tricks for solving a trig equation. And I think it'll probably be a good basis for you to do some work out of the textbook. Importantly, I can't really go through every single possible example. Trig identities, I'm going to say something very nerdy, and that is, I think trig identities are lots of fun, in that you've got the set identities that you have, and you have an equation you need to solve. And the idea is to use the identities that you've got in your toolkit, if you like, and try to manipulate the equation to try and work out the solution to whatever it is that you need to find out. So yeah, so it's just a lot of mucking about, but don't expect necessarily all the time to have a very clear pathway. Like, okay, I need to get this, so I'll just do these 4 steps and I'm done. Sometimes it's sort of like, okay, well, what sort of identities can I use in order to try and solve this problem? I'll try this one. You have a go for a while, then you realize it's getting nowhere. It's getting more complicated, not less complicated. Dead end. Go back and try with a different identity, and you try again. So it's really puzzle solving in many ways, and that's why I think I enjoy it. But yeah, so that's what you'll be doing today, a lot of puzzle solving, I suppose. But here's an example. Let's just say that you're given that tan of x is equal to, what have I got here, 5 over 12, and that x is somewhere between 0 and pi. Okay, and the question we need to answer is, what is tan of 2x? Now, I haven't written this down, but can we just take it as given that what I'm doing here is without calculator? Technically, if I know that tan x is 5 over 12, I can use my calculator to work out what x is, and then I can double the calculator value to work out what 2x is. Duh. But it won't be exact anyway. And then work out what the tan of that 2x is. And note that I don't need to know the angle. It doesn't ask me to work out what x is. It just asks me to work out what tan of 2x is. Okay, so keep that in mind. So here's the solution. The solution will take a few slides. Okay, I'm going to try and organically describe the process of thinking about what can I do about this, although my solution is going to be a bit more structured than what I say. So here we go. So I see that I've got tan of 2x, and I know I only have one identity that deals with tan, and that is tan x equals sine x over cos x. So that's what I need to be dealing with. I mean, there's no other way of moving forward other than sine x over cos x. But of course, to know what sine x over cos x is, I need to, well, in this case, sine of 2x over cos of 2x, I need to know what the sine and cos values are going to be, and I don't know those yet. Okay, so what I'll need to do is I'll need to work out sine of x and cos of x. Does anyone have any sort of ideas about how to solve that before I go about doing it? Okay, cool. How will I work out what sine of x and cos of x is? So what I do is I draw myself up a right angle triangle, and we know that in quadrant 1, it's effectively right angle trig. Okay, so I'm going to call this x hat to say it's that quadrant 1 angle. I don't know what x is yet. All I know is x is between 0 and pi. So I'm going to call this x hat, this angle here. And by standard trig definitions, I know that the opposite must be 5 and the adjacent must be 12. And I'm going to call this, I don't know, just the usual thing, C for the hypotenuse. That's unknown. Now, if you know your Pythagorean triples, you will know immediately that C is equal to, Louis? Oh, you had that look in your eyes that said that you might have known, sorry. Yeah, good, 13. If you don't, you would go something like this. C squared equals 5 squared plus 12 squared. C is equal to the square root of that. You would have to do some calculations there to work out that it's 169, and then you could conclude that C is equal to 13. Okay, but again, if you know those standard Pythagorean triples of 5, 12, 13, then you're good to go. Okay, so we've worked out that the hypotenuse is 13, and that means that by standard trig definitions, what's the value of sine x hat as a fraction? Is there anyone I can't pick on? Okay, Ollie, what sine of x hat do you think? This, Ollie. Sokotoa. Ah. Sokotoa. So sine is opposite over hypotenuse. Sorry, Ollie? Other Ollie, what do you reckon it is? Yep. So 5 is the opposite value, and 13 is the hypotenuse. And the cosine of that angle is equal to, Harrison, do you want to have a crack at it? Feel free to say no. Sokotoa. Yep, good. Brilliant. Thanks, Harrison. Okay, good. So there are angles for the reference angle. But we need to work out whether sine and cos of x, as opposed to x hat, whether they're whether they're positive or negative. So we note that tan is positive 5 over 12, which means it must be first quadrant, or all students take care, or third quadrant. X is between 0 and pi. That means it's either first or second quadrant, which means that x must be a first quadrant angle because tan of x is positive. Does that make sense? Okay, if it was set tan of x equals negative 5 over 12, we could conclude that it must be in the second quadrant, given the range of x here, and that would make sine positive and cosine negative. But they're not. They're just all positives. Hooray! So I'll go on to the next slide and just conclude that. So tan of x equals 5 over 13 implies x is in quadrant 1. Therefore, sine of x is equal to, what did I say it was? 5 over 13. And cos of x is equal to 12 over 13. Okay. So we now know what sine and cos is, but we are not after sine x and cos x. We're actually after sine of 2x and cos of 2x. Again, just to make sure those connections are there, because you kind of have to have a little bit of the goal in mind here. Tan of 2x can only be derived from sine of 2x over cos of 2x, because that's the only relationship we have, tan equals sine on cos. I had tan of x, now I've got sine of x and cos of x, but in order to get tan of 2x, I will need to get sine of 2x and cos of 2x, so I can go sine over cos. Okay, so I've got sine of x and cos of x. Let's do sine of 2x first of all. Therefore, what's the sine of 2x? Sine of 2x is equal to 2 times sine of x cos of x, which equals 2 times 5/13 times 12/13, which is equal to 120 over 169. Is that okay? So the 2 gets multiplied on the numerators to 2 5s are 10 times 12 is 120, and 13 times 13 is 169. And what about cos of 2x? Well, cos of 2x, and this is just a matter of deciding which of those forms of the identity we want to use. So I'm going to use cos squared theta minus sine squared theta, since we just have cos theta and sine theta already. But you could have chosen one of the other ones. Any of them will get you to the same path. But I'm going to choose cos squared theta. So cos squared x minus sine squared x. And that's equal to 12/13 squared minus 5/13 squared. And that is equal to, so square 12 and subtract 25, blah, blah, blah. You get 119 over 169. Okay, so that should be standard sort of fraction work, I'm hoping for you. Alrighty. So what does that mean then? It means that therefore the tan of 2x must be equal to the sine of 2x over the cos of 2x, which is equal to, I'm going to go a bit squishy here, it's equal to 120 over 169 over 119 over 169, and then I'll just go back here to finish it, just to keep it on the same slide. Okay, so I'm going to spell this out. Now from here, you might be able to just finish it off, no dramas, but I'll just spell it out a bit for those that aren't too sure about these fractions over fractions. Remembering that a fraction is just another way of expressing a division, that's 120 over 169 divided by 119 over 169, and that's 120 over 169 times, so change and flip, change to a times and flip that second fraction. And I'm hoping it's okay for you to see that you can cancel out the 169s here and be left with just ones. And so that leaves us with 120 over 119. Just a little fraction over 1 there for the tan of double the angle. And that is basically what you were asked to. Note that in all of that, I used exact values all the way through. I didn't have to approximate any decimals, which is what I would have had to have done with a calculator. And that I was able to use a number of identities together in order to get from tan x to tan 2x. So it's just a matter of piecing your way, you're making your pathway from what you know through to the final thing you were looking for, knowing that you might have to use a number of identities in order to get there. Okay, before I stop this recording and find the work I want you to do today, does anyone have any questions? So I'm hoping that means you're pretty happy with that, or after processing time, you might be happy with it. So I'll pause there, and I haven't actually worked out what page numbers that I want you to, sorry, the questions I want you to attempt, but most of them will need to be attempted, I reckon. But I'll pause there, and on the next screen, I'll write down what exact exercises I want you to do, and then they'll be uploaded in the notes as well if you need them.